Hello, I'm Austin Williams,
And I'm Taylor Williams.
and today we will be talking about the enzyme alcohol dehydrogenase. So first, a little background history. First, it was discovered in 1937 in brewer's yeast by Negeline and Wolff. It was one of the first enzymes ever to be crystallized, and many advances have been made simply throughout the 20th century since that time. Spectrometric assays have showed that there's a massive variation in the size, and analysis has showed that there's differences in the efficiency of just small gene changes. And talking about the modern time today, we see that there's a lot of variation in the kinetics and talking about the transition state and just the inhibition of the enzyme. So what I'll be talking about currently is first starting off with the structure and composition and trying to make some predictions on what we see based on our blast data. And then I'm going to talk about the function based on what are these structures. And then moving on to the active site and the function of that active site and how it works. Then moving on to the function, and then I'm going to finish off talking about the DNA sequencing since that is such a massive part of our research paper. And finally, I'll be finishing off with the kinetics and talking about how those relate to the mechanism within itself. And then I'll give it off to Taylor, where she'll talk about her research paper. So first, we see with our JS mold data and blast gene data that the enzyme is dimeric and has two subgroups. Right here on the right side, we see that we have a very large structure, basically composed of carbon chains and helical structures, and even some oxygen. And we see right here with the same thing with these yellow structures and the carbon chains. This is actually NAD+, which hints that we're later going to have a ternary complex structure that will take part in the mechanism and end up giving us a very interesting kinetics. And on here we also see with the green, and later over here with the brown colors, we see that we have a zinc ion, which hints to us that we have a metal ion catalysis within the mechanism. And then moving on to the composition of ADH, we know here that the composition is tetrameric in prokaryotes, which actually makes sense because prokaryotes are so much better at synthesizing and breaking down the alcohol, because obviously they would create it more. But it is dimeric in eukaryotes since we do possess it, but that means it's less efficient. It has a zinc cofactor based on our JS mold data, which shows us that we're actually right, and it has 375 residues in total, which actually composed mostly of cysteine around the active site, which we'll see makes sense later since it helps pull in the oxygen and alcohol group. And we know that there's actually 7 different types in humans. These are as follows. We have 3 that belong to the alpha group, the beta group, and the gamma group, and 1 that belongs to class pi, 1 that belongs to class chi, and then there are ADH 7 and 6, which are still have a lot of research being done behind them. But today we're going to focus on the first beta group, which is one of the most effective ones in humans. Talking about the function, we know with the function of ADH that it just from the name alone that it suggests that it oxidizes alcohol, which makes sense because we were talking about earlier how the NAD plus ends up picking up that hydrogen. Hammond and Schiffer and Ben Kovic in 2006 showed this and showed that it is further broken down after the process of the alcohol being turned into a ketone or an aldehyde, which helps relate back to our structure and function of our JS mold and blast data. Moving on, we see at the active site that protopuria model revealed that it does have zinc cooperation, and that the active site is full of leucine, phenylalanine, and again cysteine, which helps pull it in. So when we're talking about the zinc coordination, we have one zinc that helps stabilize it, and then we have a farther back zinc that stabilizes it further. And these multitude of cysteine residues work in the same way by stabilizing it through hydrogen bonding. The leucine and phenylalanine nonpolar groups are hypothesized to keep the active site open. You want to think of it almost like a concave structure where it's pulled in and then it's stabilized by the cysteine and again the zinc coordination. And finally, for the mechanism, thankfully we could predict the enzyme mechanism just from earlier talking about how we see that the active site will be able to pull it in, and we see that NAD+ will be able to pick up that hydrogen, which means that we have metal ion catalysis just based on the zinc coordination, and we have an acid-base catalysis because that hydrogen group is being pulled off of that alcohol and then placed on the structure of the NAD+. The releasing state is of a tertiary complex, and this has been done through Hammond and Schiffer 2006 study, who showed that the mechanism is flows very nicely and shows that it actually is picked up from the alcohol and then carried by the cysteines and then placed on. We see here with our structure that that's exactly what's happening, is that group is being stabilized and then we see that the transition state is it moving over because we have the zinc coordination and then being moved over to the NAD plus group. And then next we want to talk about the DNA and RNA sequencing. Our UniProt database shows that the ADH can manifest from 2 different DNA splices. One of them is from the 200 and 205 bend, and then the 295 binding site when it's being created and pulled off and being translated from the DNA. The RNA locus was known as NM00668, and this is shown from H.D. Edinburgh in 2007, who showed that the gene can code for different types with simple changes to the last number. Example is the residue RNA change of 48 to 370, which changes there can code for either the alpha, beta, or the gamma, different types of it, which ultimately leads to alcohols that are better at synthesizing the alcohol, which we'll talk about later in our paper. And finally, the kinetics. We were able to predict earlier that we know that we're going to have a ternary complex, which was again shown in Dickinson and Munger in 1973. This makes sense because what we have here is that either or of these can actually combine with, or either or of the NAD plus or the ethanol can combine with the alcohol dehydrogenase, and then it is then created a ternary complex where the acetaldehyde and ketones are then pulled off, and then we have the NADH that is then pulled off, which makes a lot of sense. And this also shows that the rate limiting step appears to be the final dissociation states, where that these tend to leave the complex because they might be battling, or steroids could be showing that this in fact is what is causing it to. Is what is causing it to have such trouble in getting it away, but the enzyme thankfully helps stabilize that. And now that we have some type of summary talking about what we're working with here with this enzyme, I want to move on to my partner's work in the research.
Thank you, Austin. So now that we know a little bit more about the kinetics and mechanism behind this enzyme, I would like to use this information to discuss the protective effects of the alcohol dehydrogenase ADH1B3 allele on attention and behavior problems in adolescents exposed to alcohol during pregnancy. Fetal alcohol syndrome is a condition that arises in infants following prenatal alcohol exposure and is characterized by various developmental and neurobehavioral outcomes, such as parent-child behavioral problems and poor social functioning. Dosage and timing of the exposure is key to the effects of alcohol in postnatal development, alongside other factors such as genetic risks. One class of polymorphisms, the alcohol dehydrogenase class 1B alleles, have particularly been involved in genetically modifying these risks. In a previous study on one type of the ADH allele, fetal alcohol exposure was correlated with lower mental and behavioral developments in individuals whose mothers were homozygous for the ADH1B1 allele. Babies whose mothers have at least one of the ADH1B3 alleles did not show these effects. This shows that the ADH1B3 allele is correlated with protective effects on morphology of infants postnatally, while with the Detroit prenatal alcohol exposure cohort confirming this in a previous study done. The authors of this study aim to go past the previous study done in Detroit, where they assessed individuals at 7 years old, to determine if the presence of the ADH1B3 allele continues to have an effect on postnatal development, on alcohol-related behaviors in adolescents, individuals past childhood. The sample pool for the study was 200 mother-child pairs that exhibit the ADH1B alleles, whether it was the 1 or the 3rd allele. 95% of women showed moderate to heavy drinking in this study, which is quantified as consuming at least 0.5 ounces of alcohol, which is the equivalent of 1 drink. For infants, criteria included a specific birth weight, a gestational age of less than 32 weeks, and presence of chromosomal anomalies. For assessment of prenatal alcohol exposure, mothers were interviewed regarding frequency and amount of drinking, both throughout the pregnancy as a whole and around time of conception. For the ADH genotype determination, blood was obtained from the mother by a phlebotomist via finger stick, and obtained by children either by finger sticking or venipuncture, at both ages 7 and 14. The blood genotyping was conducted at the Indiana University School of Medicine using enzymatic amplification of the DNA by hybridization with allele-specific oligonucleotides. 61.3% of the infants that were originally assessed at birth and at age 7 were also assessed at the final mark at the 14-year age. All participants were born to mothers around the age of 27 and were of the African American race, which is the race that exhibits the ADH1B3 allele in the highest frequencies. The adolescents' teachers completed an Achenbach TRF, which is a study used to assess behavioral problems on a 112-item list, and they were asked to rate the child as to how true each item was for the child's behaviors. Items were categorized in 8 general categories, including aggression, social, and attention. There were 14 control variables to isolate the actual effects of the presence of different ADH1B alleles versus other factors, such as hard drug use, age, and gender. All outliers of the data were examined and statistically controlled for analyses for each outcome, and all assessments were done blindly. 83% of the mothers in this experiment reported using alcohol during pregnancy. The ADH1B3 allele occurred in 18% of mothers and 21% of children. Only 30% of the mother-child pair showed no presence of the ADH1B3 allele whatsoever. The presence of the allele was not related to the actual rate of alcohol consumption. Consumption rates across the board, whether there was a presence of the 1B1 allele or the 1B3 allele, remained consistent for each genotype. Regressions were run on adolescents born to mothers with and without the ADH1B3 allele. Prenatal alcohol exposure was associated with significant increases in externalizing problems, aggression, delinquency, and symptoms of inattention in adolescents whose mothers lacked the ADH1B3 allele, but were not seen in those whose mothers had the ADH1B3 allele. Social problems and hyperactivity were also marked higher in those whose mothers lacked the 1B1 or the 1B3 allele. In adolescents who also lacked the allele themselves in their own genotype, prenatal exposure was also heavily associated with each of the aforementioned developmental abnormalities. Presence of the ADH1B3 allele in adolescents whose mothers also have the allele conveys the highest protective effects to prenatal alcohol exposure. Those individuals who have the allele but whose mothers do not show slightly lower protective effects, while pairs who completely lack the 1B1 or the 1B3 allele completely showed no protective effects whatsoever. Boys showed higher levels of attention deficit, social problems, aggression, delinquency, and externalizing problems than females did. While males showed higher rates of external behavioral problems, females showed higher rates of somatic complaints. These results were only exacerbated in males and females when both they and their mother lacked the ADH1B3 allele. So this was the first study done to compare the effects of prenatal alcohol exposure on behavioral problems regarding different ADH1B alleles. These findings were consistent thus far with earlier studies looking at the effects of fetal alcohol syndrome in general. Effects of abnormal behavioral development were significant in those who lacked the ADH1B3 allele, which shows a consistent protective effects throughout childhood and adolescence against abnormalities created by alcohol exposure, especially amongst boys. So we know from Austin's talk earlier that alcohol is metabolized in the liver primarily by alcohol dehydrogenase, which acts to oxidize alcohol into acetaldehyde, acting as the rate-limiting step. Class 1B ADH alleles have been found to alter rates of alcohol metabolism. The ADH1B3 allele has a lower Km value than the ADH1B1 allele, meaning that the binding affinity for alcohol to that enzyme for that allele is higher. The Kd values are also lower for ADH1B3, meaning release of the substrate from that enzyme is also greater than the ADH1B1. ADH1B3 also has a higher Vmax for ethanol than ADH1B1, increasing its potential reaction speed. For example, ADH1B3 works slowly at lower ethanol concentrations than ADH1B1, but at a high concentration it's 10 times as fast. So for heavy drinkers, much like the mothers in this study, this allele shows greater kinetic effects. Further research would be needed to determine its effects on light drinkers only. A possible explanation for this mechanism behind why it's so effective is that it causes a more rapid metabolism of alcohol, leading to higher acetaldehyde concentrations and decreases of peak blood alcohol concentration. Lower BAC means lower concentrations of alcohol that have the potential to reach the fetus through the blood, reducing fetal exposure. It is also key to note that fetal ADH1B genes are not expressed until the second trimester. So individuals whose mother had the ADH1B3 allele might actually have gotten more of their protective effects early in fetal development from the mother, rather than their own presence later on in life. However, it is also key to note that having the presence of that allele in the adolescents themselves also exhibits protective effects postnatally throughout adolescent development as well. More studies are needed to determine the clearance rates of alcohol for this variant of the enzyme and whether this enzyme elicits the same effects in both low and heavy alcohol consumption by the mothers equally. But it is key to note that pairs that have the mother both has the 1B3 allele and the child show the greatest protective effects overall across the board. Between enzyme kinetics and mechanism, the ADH1B3 is correlated with decreased likelihood to develop alcohol-related disorders. Overall, the study shows that prenatal alcohol exposure elicits developmental qualities that persist well into adolescent development, but that the presence of at least one ADH1B3 allele, whether it be in the child or the mother, can decrease vulnerability or exhibiting these abnormalities, though the exact mechanism behind this is still relatively unclear at this time. We hope that you enjoyed our presentation on alcohol dehydrogenase, from its history, mechanism, and kinetics, to the role that its multiple alleles play in development of fetal alcohol syndrome.
Thank you for listening.
Thanks.
And our citations.
Pretty.
Rock on.